Hi there. So the final part of the buffer section is the mathematics of adding that acid and adding that base to a buffer. Now, this has been explicitly said that it will not be tested on the AP exam, but the calculations are the same as calculating the pH during a weak acid or weak base titration, which are. So it just makes sense for us to get a little bit of practice with these type of calculations, as they are pretty much the most complex calculations that we will do all year. So this would be adding a strong acid or a strong base to a buffer solution. And we've already talked about this in like non-mathematical terms, that what happens? Well, if I add a strong acid, the acid will react with the weak base, part of the buffer solution. It will create more of the acid with the hydrogen attached, and then I will have new concentrations of those acid and conjugate base, and I can just use regular Ka or the Henderson-Hasselbalch equation to figure out the pH. The beginning part of this is going to be what we call a Bca chart. So just like we did maybe in first year chem with stoichiometry, we are going to basically do a stoichiometry calculation to figure out how much acid is produced or how much base was produced, then divide by the new volume, if there is one, to find a new calculation, to find a new concentration, and then do the equilibrium calculation. So there's two parts to all these problems. There's a limiting reactant part, which we're going to do with a Bca chart, and Bca chart is always done in terms of moles. And then we are going to do an equilibrium part that is always in terms of molarity. That's going to be a big deal. So here's the first problem. A 1 liter buffer solution with 0.14 moles of cyanic acid and 0.110 moles of potassium cyanate. And there's the Ka. And so we want to find the pH of this at the beginning. And then what we'll do is we'll do the pH of this after we add some acid and the pH of this after we add some base. So the pH of this is a normal buffer question that you have just done. So if you wanted to pause here and see if you could find the pH of this, you should be able to. It's what we've been doing in the past few videos. So I'm just going to start out with a general acid. A general weak acid reacts with water, make H3O plus and the conjugate base. I know I start with 0.140. It says that many moles in 1 liter of solution, so I can say I can do this in molarity. This is 0.110. There's 0, and we don't ever worry about the water. This guy goes down by x, up by x, up by x, 0.110. Now we use the Ka to solve for the H3O plus and then the pH. The Ka is 3.5 times 10 to negative 4. That equals X, the H3O plus concentration, times 0.110 over 0.140. X is equal to 4.45 times 10 to negative 4 molarity. Of course, that's equal to the H3O plus concentration. pH is equal to the negative log of that. And that equals 3.35. You can also always use the Henderson-Hasselbalch equation for this, right? If you were going to use that, it would be, pH equals the pKa, so the negative log of 3.5 times 10 to negative 4 plus the log of 0.110 over 0.140. It comes out to be the same number. So that's the kind of the starting pH of the buffer. Now let's take a look at what happens when I add the acid to it, right? I'm adding this much acid. So we know the pH should change. The pH should go down, but it's not going to go down by that much. Okay, and so the first part of this is always stoichiometry, so Bca, done in terms of moles, not molarity. and then we will find new concentrations if need be, and then do an ice chart. So when we add the acid, right, what is that going to react with? Well, it will react with the conjugate base. So the CNO negative will react with the H plus, and notice, since that's a strong acid, this is a full arrow here, and it will make HCNO. So what am I starting with? I start the conjugate base is going to be 0.110 moles. Then the question tells me I add 0.015 moles of that strong acid, and I would start out with 0.140 moles of my weak acid. And the strong acid gets completely used up. So this guy goes down by 0.015 moles. And its other reactant will also go down by 0.015 moles, and the product will go up by 0.015 moles. Right? This is not a weak acid reacting. This is a strong acid, where the purpose of having this buffer solution is so that we could have that weak acid in there to react with any acid. The purpose of this buffer is so that there is some conjugate base to react with the acid that we add. So now our final concentrations will be, or final number of moles is 0.095 moles of that conjugate base. We have no more of that hydrogen ion. It has been consumed. And we have 0.155 moles of that weak acid. Now, the second part of this is using your answers from what we just did to do an ice chart and calculate the new pH. Remember, this is done in molarity, so you may have to divide by the total volume, and you would just do that if the question said, instead of you're adding this many moles of acid, if you add this volume of this molarity acid, you would need to account for that. This question did not tell us. It just said we added this much H plus. So I'm still just going to assume everything is still 1 liter. It doesn't give us any information to do anything different. So this is the HCNO plus water, right? This is the regular formula for a weak acid reacting as a weak acid. Right? I could still think of this as like dividing by 1 liter. So my weak acid is 0.155 molarity, right? The acid has all been used up. So think about, now we're starting with 0 H3O plus, and this is 0.095 molarity. And weak acids, we know that it is negligibly going to actually dissociate 0.155 right? And then what we need to do here is find the pH of this system. The Ka is 3.5 times 10 to negative 4. That equals X times 0.095 over 0.155. Solve for X, which is equal to the H3O plus, and that is 5.7 times 10 to negative 4, or the pH of this solution is now 3.24. Remember, what we found was that at the beginning, this buffer with nothing added was 3.35. And now we've added all this acid, and we get a pH of 3.24. If I had added that same number of moles, right, 0.015 moles to 1 liter of solution, just if it was 1 liter of water, the pH would drop from 7, which is the pH of water, all the way down to 1.8. But I take that same amount of acid and add it to this buffer solution. Yes, the pH does drop, but it drops less than, what, a tenth, about 0.11 of a pH unit. So buffers really do work. The next one of these is the exact same problem, except this time we're adding a base. So what does the base react with? The base reacts with that weak acid. So it's going to be the HCNO that reacts with the OH minus. It will make, and you can see that in your notes, I put a water column, but water column we don't ever need, and it makes CNO negative. What do we start with? 0.110, again, moles of the conjugate base, 0.140 moles of the weak acid, and 0.015 moles of that strong base. The strong base gets completely consumed by my strong acid. And it will produce that same 0.015 moles of the conjugate base. Both of these come out to be 0.125 moles. And of course, I use up all the base that's added, so that turns out to be 0. Now I take my last row and I use that in an ice chart. Remember, ice charts are done in molarity, so I divide by the total volume, but the total volume is 1 liter. So I just take my regular, I just went back to writing it as just HA. It really doesn't matter. The weak acid concentration is 0.125 molarity because we're dividing by 1 liter. Water doesn't count. Weak acids only negligibly dissociate. So now the Ka, 3.5 times 10 to negative 4 is equal to X times 0.125 over 0.125. And of course those guys cancel out. So X, which is the concentration of the H3O plus, is equal to 3.5 times 10 to negative 4, and the pH is equal to 3.46. So did the pH go up? Yes, of course the pH went up. We were adding a base, but did it go up very much? No. If I added that same base to pure water, the pure water would start with a pH of 7. That solution would have a pH of 12.1. But I add it to a buffered solution, the pH goes up, but very little.